With this video, we're going to focus on the conditions for special parallelograms. In particular, we saw the structure in our earlier lessons where we started off by saying this shape is a parallelogram, and now here are a bunch of facts that we know are true about it. We also saw then that those facts work backwards, that we could take a checklist of items and say, if this stuff actually works, you can bet your grandma's life, be absolutely certain that something actually is a parallelogram. Well, just a little bit ago, we saw that special parallelograms, rectangles, rhombuses, and squares, also have some extra properties about them. And now we'll see that those properties work backwards, that you can actually say, is this thing a rectangle? It looks like it is, but how can you be absolutely 100% certain that it is? Something can look like a rhombus, but how do you know, or what do you need to know to be absolutely certain that it actually is? That's the focus of this one. We will look at those criteria and be able to explain why a shape is a rectangle, a rhombus, or a square. And starting off, we've got 5 theorems. These are the 2 that we have for rectangles. And of course, I've got the symbolic logic written up on the marker board. Essentially, one right angle is all we need. If we have a parallelogram, and then we also get one right angle, it's going to force the other 3 angles to also be right angles and give us a rectangle. If we've got a parallelogram and we have the diagonals congruent to each other, that will force it to be a rectangle. In terms of rhombuses, if we have a parallelogram and we can show that there's one pair of consecutive sides that are congruent, that will actually force all 4 sides to be congruent, making it a rhombus. If you can show that your parallelogram has a set of perpendicular diagonals, that will force it to be a rhombus. Or if even one diagonal in a parallelogram will bisect the opposite angles, that forces it to be a parallelogram. But I want to emphasize something on every last one of these. A parallelogram width, a parallelogram width, a parallelogram width, parallelogram width, parallelogram width. Every single one of these things requires you already know this is a parallelogram to begin with, and then is it a special type? Well, of course, if it's not a parallelogram at all, something can't be a rectangle if it's not a parallelogram at all. We do have to make sure that we do have these parallelograms, which of course is why we spent all our time, since every last one of these needs a parallelogram. That's why we had the earlier homework on those 6 different methods, those 5 different methods of, is this a parallelogram, yes or no? We had one entire homework question devoted to this one set. In order for something to be a parallelogram, we had our 6 different tools. We know that you can get parallelogram by getting 2 pairs of opposite sides that are parallel, 2 pairs of opposite sides congruent, 2 pairs of opposite angles congruent, 1 pair of opposite sides that are both congruent and parallel, 1 angle being supplementary to 2 different angles, or having the diagonals bisect each other. We will still need to use this list of tools to explain why something is a parallelogram, and after using this list of tools to get parallelogram, we will use this list of tools to say what kind of special parallelogram. And so we'll launch right into it here. Manufacturer builds desks, and their mold has AB congruent to CD. Okay, so AB and CD are congruent. That's 1 pair of opposite sides. We also have BC congruent to DA, a second pair of opposite sides congruent. Well, please notice these two things with two pairs of opposite sides congruent, that was one of the conditions to give us a parallelogram. This information in the blue says we've actually got two sets of parallel sides. Why does it have to be a rectangle? Well, the next piece is the measure of angle ABC is 90. That's one right angle. We have a parallelogram, and we have one right angle. This is one of our tools that we've got. A parallelogram with one right angle forces the shape to actually be a rectangle. And we're done. We can actually reference the two pieces of the two theorems that we're using, and those are our justification. This is our explanation why it's a rectangle. Consider this one. Determine if the conclusion is valid. Okay, so the conclusion is this shape is a rhombus. For it to be a rhombus, one of these tools has to work. These are the three different tools we have to say, I know it's a rhombus. And so we're just going to go through and check. If one of them works, the conclusion is valid. If none of them work, then we don't have enough evidence to say that we know that it would work. So let's run through the problem. Okay, EF congruent to FG. EF congruent to FG. Please notice what that tells us. We have one pair of consecutive sides that are congruent. That's still not enough, though. We have to make certain that we actually do have a parallelogram. If it's a parallelogram and we've got the congruent sides, together those two things force it to be a rhombus. So we need to continue then. EG perpendicular to FH. Okay, EG being perpendicular to FH tells us that we've got a boatload of 90s up here in the middle. Is that enough to conclude that we have a parallelogram? Essentially, this is telling us the diagonals are perpendicular. Perpendicular diagonals, is that on our list of ways to get a parallelogram? No. We would need to have the diagonals bisect each other to get a parallelogram. Crossing at a 90 doesn't do anything for us, so we don't know that we have a parallelogram. We don't know. Since it's possibly not a parallelogram, this is not a valid conclusion. It might be wrong. And it could be wrong simply because what if we were to extend this piece out longer? There's a shape traced out in the red that fits all the conditions, but is obviously not a parallelogram, so obviously not a rhombus. Without knowing those lengths, or without knowing some more information, we can't do anything. So, whoa, that didn't mean for that to happen. What additional information would we need? How could we fix it? Essentially, that's saying, how could we make sure? What piece of information could we put in that would tell us, now we know we actually do have a parallelogram? And it's worth noting that there is a lot There are many, many different correct answers to this one. The first one that pops into my mind, if opposite sides are congruent, that'll force you to have a parallelogram. So what if these two things are the same? If we had FG congruent to EH, that would then force, since these three all match, we wind up getting all four. This one piece of information gives us the rest of it. And so that's one way to get it. There are, of course, others. If you simply said, we need EFGH to be a parallelogram, that's another way that we can do it. What about this problem? Same directions. Making the conclusion that EFGH is a square. Does that have to be true? To be a square, it has to be a rectangle. It has to be a rhombus. It has to be a parallelogram. So let's start running through and see what we have. EB congruent to BG. EB and BG are the same. FB congruent to BH. These two things show us that the diagonals bisect each other. And we know from our earlier work that if a diagonal bisects each other, if the two diagonals bisect, that piece of information in the blue tells us that we have a parallelogram. Okay, now that we know it's a parallelogram, we have to go through and check. Is it a rectangle? Is it a rhombus? Okay, changing colors. EG congruent to FH. EG and FH. The two diagonals are congruent. So it's a parallelogram. The two diagonals are congruent. That's right here. Parallelogram, congruent diagonals. So yes, we have a rectangle. It's a parallelogram, it's a rectangle. And next we'll check here. Triangle EBF. I'm going to clean this up a little bit so you can see it easier. EBF is congruent to EBH. Those two triangles are the same. Which of course means all their matching parts are the same. Those two sides would have to be congruent. Which then gives us a pair of consecutive sides being congruent when we already had the parallel. So these observations in the yellow tell us it's a rhombus. Well, since it's both a rectangle and it's a rhombus, that makes it a square. So yeah, that is a valid conclusion. And then here's our last problem, though admittedly it's a long one. Use the diagonals to determine if this thing is a rectangle, a rhombus, or a square. Okay, so here's our challenge. We're going to start by noting the directions here, whether a parallelogram with these vertices. These directions are telling us this is a parallelogram. We don't have to check for that. We're told it is. And so really the only things that we have to start checking for, if we've got one right angle combined with being a parallelogram, that's going to give us our rectangle. What would you need to have a right angle? Well, to get a right angle, we know that perpendicular comes from having negative reciprocal slopes. If we want to verify this way, we could check for opposite reciprocal slopes on two of the sides. If the sides have perpendicular slopes, opposite reciprocal, that gives us the right angle, which would force it to be a rectangle. That's one way to check for it. We also had a second method that the diagonals can be congruent. The parallelogram combined with the perpendicular with congruent diagonals is a second way to check if this thing is a rectangle. Well, how would we show that the diagonals are congruent? We could use the distance formula on those two diagonals. And if the distance formula tells us that those are equal, we've got that. We could use either one of these things and check. Both methods are completely valid. It's completely up to you as to which way you want to do it. So which way looks easier? Checking one pair of slopes or one pair of lengths? I agree with you. I think slopes are easier than lengths. So that's the approach. Because slope is easier, these are the ones that we're going to go for. Okay, so wiping this out to create some room, we're going to check to see if they actually do have opposite reciprocal slopes. And so checking our two sides, PQ would be a side. It, of course, is going to connect over to QR. So checking the slope of PQ, we'd have 6 minus 5, negative 4, subtract 2, which gives us 1 over negative 6. Checking the slope of QR, 5 subtract negative 1, 2 subtract 3, gives us 6 over negative 1. So, are those slopes opposite reciprocals? Definitely reciprocals, 1 over 6 and 6 over 1, but are those opposites? No. They're both negatives. And because they're both negatives, we know that they're not opposites, so since those are not opposite reciprocals, we know that it's not a rectangle. Well, of course, since it's not a rectangle, it can't be a square if it's not a rectangle. So, there. It's a little bit closer to a square. Well, just by checking this, we're able to rule out a couple of things. Not a rectangle, not a square. Could it be a rhombus? Now I'm going to erase all of this stuff and come back to, so that way we've got some room to work with. If we are going to have something be a rhombus, we've got 3 different techniques that we could apply. If we have one pair of consecutive sides congruent, that'll give us our rhombus, since it's already a parallelogram. Well, if we're going to go with a pair of consecutive sides being congruent, that's going to need the distance formula twice. If we have matching or equal distances, that gives us our congruency. Another thing we could do, if the diagonals are perpendicular to each other, that'll give us our rhombus. Well, to get perpendicular, that's one that would need opposite reciprocal slopes, not on the sides, on the diagonals. So of course we're faced with the same decision. If we wanted, we could go through and get a distance formula to check if the sides are the same length, or we could grab the diagonals and check to see if their slopes are opposite reciprocals. Both methods will get us there. It's just picking the one that you want to go with. So which one do you want to do? Do you want to do slopes again, or do you want to see how we can use distance? Right? Since we're picking distance, we would have to take consecutive sides, and since I already did PQ and QR last time, why not just use those consecutive sides again? All right, so we know the distance formula is essentially the Pythagorean theorem. And so we'll start off here, our distance PQ. Okay, so we had -4 subtract 2, and we had 6 subtract 5. Okay, so -4 subtract 2 equals -6. -6 quantity squared, 6 times 6 is 36. 6 subtract 5 is 1. 1 squared is 1. And so when we put this into our into the distance formula, that length would equal the square root of 37. Checking the same thing now for QR. We'd have 3 subtract 2 and -1 subtract 5. Right, so that's 3 minus 2 equals 1. 1 squared is 1. -1 subtract 5 would equal -6. Squaring that still gives us 36. And it comes out so that they are equal. Because those consecutive sides are equal in length, we know that they are congruent. So yes, this thing is a rhombus, but not a rectangle and not a square. And we're done. Either way, we've got a choice of using the distance formula or using slope. Both methods are valid. It's purely a matter of which one you prefer. If it were me doing this, I wouldn't mess around with the distance formula at all because it's more writing. For me and the way I think, slope is faster, it's easier. That's the way I would do it because it's what clicks with my brain. I've had plenty of students in the past that prefer distance formula. It's what clicks for them. Whichever one makes more sense in your head, go ahead and pick the easier method because we have the freedom to use whatever works. Ultimately, though, the key characteristics are that you know this list of 5 tools and you can apply them to say, this thing is a rectangle, here's why. This thing is a rhombus, here's why. Both of those come from the fact that you already have a parallelogram, so we're using our previous knowledge. This is a parallelogram, here's why, followed by this stuff makes it special. if it works at all.